Okay, so let's start today's lecture. I will be starting with a brief revision of what we had done yesterday. Yesterday, we had seen the various types of block ciphers, that is, the various modes of operations of the block ciphers. And just before that, we saw the basic difference between a stream cipher and a block cipher. We also saw the basic model of how a block cipher works, and then we started off with the various modes. So, if you remember, we had seen three different modes of block ciphers so far. We started off with what exactly is the electronic code book, that is ECB. Then we saw what is CBC, that is cipher block chaining mode. And finally, the third type, that is cipher feedback mode. So I will quickly revise the first three modes once again, just to recap what we had done yesterday. Fine. So in the next 2 to 3 minutes, I would be revising whatever we had done so far, whatever we have seen so far, and then I will start off with today's topics. Fine. So let's start off with this one, the electronic code book. It is one of the simplest of all the modes we have seen so far. There is a plain text. It can be of n number of bits. What we need to do is we first of all need to divide it into into a size. For example, there are 60. For example, there are 64 bits in a block. So what I would do is I would first of all convert the plain text into so many blocks which could accommodate 64 bits. Fine. So what I will do is, suppose my plain text is of size 1000 bits. I would divide that with 64, and somehow I will take those many number of blocks. For example, if it comes out to be somewhere, just I'm just giving you one example. It is not accurate. For example, it comes out to be third now 11 point something something. So what you can do is you can select the fraction, that is, if it is 11 point something, then you should take one extra than that. For example, you can take 12 blocks. Just an example I'm taking. So what happens is, first of all, you need to divide the plain text size by the what you can say block size, or the number of bits in a block, and then whatever answer you get, whatever fraction you will get, mostly you will get in fractions, add 1 to the whole number so that it becomes a complete factor or multiple of that block size. Am I clear? So whatever will be the answer plus 1 will give you the number of blocks. So obviously the last block will not have exactly those many bits. So what you need to do is you have to make sure that the last block should have some padding bits or some random bits so that it becomes a multiple of the block size. Am I clear? It's very simple. Whatever be the plain text, divide it into those many blocks, take it as one of the inputs, and the second input would be the key. Now we also saw that the key in this case is a symmetric key. Symmetric key simply means the same key will be used again and again for the entire process of encryption as well as for decryption. So according to this diagram, it's very simple. You provide one plain text, you provide one key, and encrypt it using some functions. We are going to learn what are those functions in today's topics. Okay, and afterwards you will get a ciphertext for the block one. In the same way, you have to repeat the entire process for those many blocks you're having. And at the end, when you concatenate each of these ciphertext block one, block two till block n, you will get the final ciphertext. Is it clear? Yes or no? Kindly let me know. I'm just revising the topics once again. So in case you missed it, or in case you were not paying attention, just have a look. Or in case if you are having any doubts, kindly clear it right now. Fine. So in the same fashion, the decryption will also work. Over here, the inputs will reverse. That is, the input will be the ciphertext and the key will remain same. We have to apply the same for a function over here in the reverse order, and you will get back the plain text. It's one of the simplest modes of operations of block cipher. So this is what we call as the electronic code book. Now next up, we saw the second type, which is the cipher block chaining mode. So what happens in this? There is some concept of a chaining. Now over here, as you can see, C1 is the output that is being sent as one of the inputs to the next block. That is, it will be C of 1. So in general, we can say that for the nth block, the ciphertext input will be Cn minus 1. Am I clear? So this is what we are doing. There is a plain text block, and we take a initialization vector of the same size as that of the plain text. So if my plain text is of size 32 bits, I would select the initialization vector also of the same size, that is 32 bits. Because at the end we are XORing the initialization vector IV with the plain text PT or P1. Fine. Whatever is the answer for that operation, we will encrypt that using the key K. And whatever result we get, that is our ciphertext C1. Now this is one round, one block. So the output of this block will be sent as the input of this XOR operation for the next round. That is for the next set of plaintext P2. Am I clear? And this process will keep on continuing until the n minus 1th round. And finally, we will get again the ciphertext. We have to combine them, concatenate them, and we will get the stream of ciphertext. Fine. This is the encryption part. So the exact reverse will happen in the decryption part also. One of the inputs will be C1. We will go in the reverse order. Now we need to decrypt with K, and whatever result we will get, we have to XOR that with the IV, the same IV, and we will get the result for the first block of the ciphertext, that is P1 being the plain text. Fine. Entire process will keep on repeating, and at the end we will get the whole plain text back. Any doubts with this? Is it clear? If you're having any doubts with this, kindly let me know. By the way, everything is running smooth. If any jitter or any lag is there, kindly let me know. Fine. Any doubts with this? Or can I move ahead with the third type? I'm quickly revising the third one. I guess few of you might have issues with the third one because uh, it's a little complex to understand as compared to the previous two types, right? So let me focus on this third type. The third type is very simple, no issues. Only thing is you might get confused in the third block or the third functional block over here. So what happens is you have to start with an initialization vector. We are assuming that the initialization vector is of 64 bits. So we will copy that into a blank shift register. It's basically a temporary variable, a register basically, and you're copying the initialization vector bit by bit onto that shift register. Fine. Now what we are doing is we are encrypting that shift register with the key, whatever key you have agreed upon, and the result is the encrypted shift register. Am I clear? Clear so far? So I'm repeating again, you have to take an initialization vector of size 64 bits because over here we are placing that in a 64-bit register. So we are assuming that it is of size 64 bits only. And we are encrypting that shift register with a key, whatever is the result that is present inside this block, that is encrypted 64 bits shift register. Am I clear? Clear so far? Kindly let me know. Yes? Okay, so let's move ahead. Now what we are doing is whatever is the output, that is whatever is this encrypted 64 bits, from that I have to select S bits. Now I told you a very clear-cut formula. You can select S bits. I'm assuming S to be 8. Why I'm selecting 8? Because 8 is a multiple of what you can see, 64 can be divided by 8. Or in simple terms, we generally keep the sizes in terms of powers of 2 or powers of 2 basically. So it could be 8, 32, we can say 64, right? So I'm selecting the most common size, that is 8. So what I'm doing, I'm selecting 8 bits from this encrypted 64 bits shift register. Now depending upon the sender and the receiver, they can choose any of the ways of selecting the 8 bits. What they can do is they can select every 8th bit, right? They can start with 1, they can start with 8, then they can start with 16 and so on. Or what you can do is you can select the first 8 bits that you encounter from the MSB side. Am I clear? It entirely depends upon the sender and the receiver. They have to agree upon a method. We are not focusing on that. We are simply saying that you have to select 8 bits from this encrypted 64 bits shift register. Am I clear with this? How to select those 8 bits? I guess this was a little tricky to understand yesterday. So I'm repeating it once again. Am I clear now? Any doubts with this so far? Fine. Okay. A division? Okay, fine. So what we need to do next is, now we know that, as I had already told you, that this particular mode of operation is basically like a stream cipher only. What we are doing, we are dividing the 64-bit plain text into smaller stream ciphers, each of 8 bits. Am I clear? The same thing I had told you yesterday. So what happens is, as you can see over here, we have selected 8 bits over here. So we need the plain text also of the same order. Otherwise, we can't XOR it. So for that purpose, what we are doing, we are selecting the first 8 bits of the plaintext as P1. And then we are XORing that with these 8 bits or S bits that we have extracted from the shift register or encrypted shift register. Am I clear? And then we XOR it. Whatever is the result, that result is sent as one of the inputs to the shift register. Now, whenever I'm saying one of the inputs, now it is very clear that we can't place 8 bits into 64-bit register. So we need to do some changes. So for that, what we are doing is we are shifting the existing shift register, which is of size 64 bits, to the left by 8 bits, or in this case, in general, S bits. Am I clear? So if I shift it like this, so there will be a void space of 8 bits left over here. That 8 bits will be filled with the result of the previous step. Am I clear now? Is it clear? The encryption part? Kindly let me know. Yes, A division, B division. I guess this should be clear now. Fine. Okay, cool. So again, the same thing will happen and it will keep on continuing till the last block of 8 bits. And finally, we will get the ciphertext. So I guess the encryption part is simple to understand. The decryption is also very simple. It has a relationship with the encryption, um, as simple as that. So what is the relationship? We are going to start with the IV. We need to decrypt it because this time we are decrypting with the same key. Now here, I guess this is where you might have faced issues or confusion. It is very simple. Don't look into it from the discarding purpose. From the discarding point of view, it is very simple. What we are doing is you can simply focus on this part, that is select S bits. Am I clear? What you are doing is, like in the previous case also, we had selected the S bits. Over here also, we are selecting the S bits. We are not bothered about the remaining B minus S bits. That is why it is mentioned over here as discard the remaining bits. So you don't need to worry about the remaining bits. You need to focus only on the S bits. That is the bits we had encrypted while the encryption process was going on. Am I clear? So the same 8 bits you have to select. And why I'm saying same 8 bits, it simply means whatever mechanism you had used. That is, select the first 8 bits or select every 8th bit. That same mechanism you have to use. And depending upon that, whichever 8 bits you will get, the result is those 8 bits only. Am I clear with this now? This is where I guess you might have faced some issues. So I am focusing on this once again. Am I clear how to select those 8 bits? Come on, quickly give me your answers. So whatever method you had used while encryption, the same technique you have to use over here also. And depending upon that, you will get hold of those 8 bits. And now as we are decrypting, we have the input as the cipher, right? So the cipher will be basically the C1, that is C1 is nothing but 8 bits. So we can XOR that, and whatever is the result, that will be my plaintext P1. Am I clear? So the same thing will go on for the next round as well. As you can see over here, the output, that is C1, was sent as one of the inputs to the next block. In the case of encryption, the same will happen over here. C1 only will be sent as input to the next block, and the same process will repeat again and again till we reach the final block. So I guess this is now clear how to proceed ahead with this sort of a block mode of operation. Fine. So if everything is clear, can we move ahead with the fourth and fifth one? Do let me know. Yes? Okay. Okay, fine. So I have used a 15 minutes, but it was very important. Otherwise, you won't understand the next few modes of operation. So let's start with the fourth one. Fourth one is what we call as output feedback mode. Now just have a look at this diagram and try to compare this with the previous one. Try to compare this with the previous one and let me know what is the difference between this one and the previous one. This is what we call as output feedback mode, and the previous one was called as, you only tell me, cipher feedback mode, right? Just have a look. How is it different from the previous one? There is a very minute difference. Just have a look and let me know what is that difference. Have a look at the diagram. Yes, come on quickly. It is visible, right? So kindly let me know what is the difference. almost everything looks similar. So what is different? No. Key is also same. Have a look at the diagram, Harsh. Check the diagram properly. There is a very minute difference. Output, okay, but what is that output? Jay Panchal is saying output, correct. Simran is saying output is given rather than the ciphertext, correct. That is the basic difference of this mode of operation. If you see, random bit is taken, Harsh. Random bit is obviously taken in each of the case. The only difference is correct. Encrypted key को ही भेजा है as output. Not encrypted key, it is the encrypted shift register. If you see it properly, the encrypted shift register is sent as input to the next round instead of the ciphertext. Is it clear? A division, B division, come on, have a look. Again, look at it properly. The encrypted shift register is sent as the output to the next round instead of the ciphertext. Am I clear? Fine. Why is it done so? Can any one of you tell me why is it done so? These are very minute changes, but it causes a lot of difference in the final output. Just have a look and let me know why we are opting for this. Yes, B division. Yes, students, come on. There's a very minute difference, but what is it? There might be some weakness in the previous case, right? That is why the change has been made over here. What could be that weakness? If we compare this with the previous case, then what could be the difference or what could be the weakness? Come on, quickly give me answers. If I think of this, the previous one that is CFB, cipher feedback mode, then how is it different or why basically this has been updated with the with the next model or next mode? Any ideas? Come on, be interactive. I know it is the last lecture of the day, but still can't help it. Come on, give me answers. Yes, students, let me know your answers. I'm audible, right? So come on, give me answers. In this one, the encryption is done blockwise. Harsh, both of the ciphers are encrypted blockwise only. But if you see carefully, in this case, that is in the previous case, that is CFB, the output of the XOR operation was sent as the input to the next step. Am I clear or not? B division, Siddhi, Simran, Shreya, Swarda, Rishikesh. A division, Jay, Harsh, Rohan, Deep. Is it clear? So, what could be the issues with the third type, that is cipher feedback? What happens is if there is a minute error in the XOR operation, for example, if there is even a minute error, or if a 0 bit turns into a 1 bit or a 1 bit turns into a 0 bit, whatever. You must have studied about burst errors, single bit errors in CN, right? So similar kind of thing over here. So if any error happens in the CFB mode, then what happens is the same error will be propagated to the next round and it will keep on adding to the errors. Yes or no? Yes, correct. So to avoid that, what is being done is the output of the previous step, that is output of the encrypted IV, those selected S bits, that only I am sending as the input to the next round. So what happens is if there is any error due to the XOR operation or due to some burst errors, they will be confined to this block only, and they will not be mitigated. Sorry, they will not be transferred to the next block. Am I clear? This is the basic change. This is the basic difference between the previous one and this one. A very typical question from the Viva point of view. Why have we replaced the CFB mode with the OFB mode? I guess now you are in a position to answer this question. Yes or no? Kindly let me know if you got the understanding of this. Fine. Okay. Okay, great. So this is one of the reasons. So what we are doing is after selecting those A's 8 bits or S bits in general, we are sending those as the inputs to the next round and the entire process will remain same. Similarly, in the decryption side also, as you can see, it is slightly different. It has to be different, obviously, because over here, the IV will be decrypted with K. And now check what is the difference. In the previous case, if you compare this with the previous case, we had to select those 8 bits and then we had to decrypt it with the CN. But in this case, we don't need those S bits, yes or no. Because in the previous case, those S bits were XORed with the plain text to get the cipher text. But is it so in this case? Yes or no? Kindly let me know. Do we need to select those S bits and then XOR it? No. Clearly, we don't need that. Why? Because we are not XORing the S bits anymore. We are simply sending them as an input to the next round. So what we need to do is we simply need to take the output of this step and XOR it with the cipher text. We will get the plain text. Am I clear? So we don't need to worry about the S box, etc., etc. Because ultimately you will get those values only. Ciphertext will be of the same size and this will be of same size only. By default, you will get 8 bits only. Am I clear or not? Yes or no? Any doubts? Fine. So can we move ahead? Kindly let me know. In the previous case, there was a typical block where we had mentioned that we had to select the S bits only and then discard it, whatever we had to do, and so on. But in this case, as you can see, by default, we are XORing it with C1. If C1 is of size 8 bits, we have to select the first 8 bits by default. Otherwise, we can't XOR it. Simple enough logic. So we have no need to arbitrarily mention that you have to select S bits and then carry on the operation. It's very clear, I guess. If the C1 is of 10 bits, we have to select 10 bits. If the C1 is of 20 bits, we have to select 20 bits, first 20 bits, and so on. Am I clear now? Is it clear now? Kindly let me know. So depending upon how many bits you have selected, during the initial operation, the same you have to select right now also, because as it's an XOR operation, you can't compare an 8-bit value with a 20-bit value. You need to have both the values same. Fine. Now can we move ahead with the last type, which is counter? Do give me an acknowledgement, then I can move ahead. Fine. Okay. Okay, thank you. So let's focus on this type, last type, and then we have to start with the next topic. It's one of the simplest. It's again quite similar to the previous case. Just have a look what is happening over here. Instead of an initialization vector, we are simply replacing that with a counter. Now what happens is in the future you will see some attacks. For example, race conditions, or there could be some attacks in which the user or the attacker might try to replicate or replay your existing passwords, or they may try to replay your existing packets. So what happens is replay attack is one of the attacks where the attacker may try to copy or may try to gain access to your communication by repeating whatever you had sent previously. For example, if I'm trying to access my Gmail account, I will be entering my user ID and password, and that will be sent to the server. So what can happen is the attacker may anyhow gain access to the communication. They may capture your packets, and he or she might try to replay the same attack, the same communication in the future also. That is what we call as a replay attack. With the help of the counters, what we can do is we will assign some timestamp, or we will assign some integer values for that particular block. So for block number 1, it will be basically using counter 1. For block number 2, it will be using counter 2. So what happens once a counter is used, it will not be used again. Am I clear? Counter 1 can be used only once. Counter 2 can be used only the second time for one time. That is basically counter 2 will be used only once, and so on. What happens is time is constantly moving. Time doesn't stay the same, right? So if I carry out an operation at 5:01 p.m., the next operation would be obviously having a different value. It could be 5.011 or 012, whatever. Am I clear? It can't start at the same time, or even if it starts, it will be very difficult for the attacker to capture the same packets again and again and carry out the operation once again using a replay attack. Am I clear? Am I making any sense? Kindly let me know. So just to avoid any replay sort of an attack, it is basically the fifth and we can say the most advanced type of block operation or block mode of operation. What happens in this is we are basically trying to avoid any replay sort of an attack just by adding the extra bit of security that is what we call as the counter. Am I clear? So once I have used one of the counters, or in simple terms, you can compare this with OTPs. OTP, full form, one time password. It can be used only once, right? So we can't make use of the same OTP again and again for the same transaction. Is it possible? No. If we try to reload the page, you will get a fresh OTP. Similar sort of a concept. Am I clear? Any doubts with this? Fine. A division? Okay, fine. So similar kind of a concept. Let me show you the description of this. It is similar to the previous case only. The difference is that it uses counters or sequence numbers. Obviously, once it's very easy, it's very simple to correlate this with tokens. Once you give a token to a person, that person will have a unique token from any other person in that queue. Am I clear? So the person just after me will be having a different token number, +1, +2, and so on. Fine, we are incrementing the token numbers. Similar to that, no two people can have the same token, and as a result, there will be very less chance of the attack of the decryption taking place from the attacker's point of view. Clear? What we do is we put a constant value as initial value of counter, which will be of the same size as that of the plaintext block. Obviously, the size has to be same. We encrypt that with K, and whatever is the result, we XOR it with P1, and then we get the block of ciphertext as C1. So this could be of entire 64 bits only. This could be of any size, 64, 32, 16, whatever is the block size, the same block size could be present over here also. Am I clear? And at the end, we will get the ciphertext. The reverse process takes place at the decryption side. Exactly same and very much simple to understand. The counter 1 will be again used to decrypt, and then C1 will be XORed with the result of this, and we will get the plain text back. Am I clear? Any doubts? Kindly let me know. Yes, come on, students. Any doubt with this? Kindly let me know. Clear. Okay. What about B division? Fine. So now we have seen all the 5 modes of operations. I will quickly give a brief review of this, a summary, you can say. Electronic code book. In ECB, we saw that we have to separate, or we have to divide the entire plain text by first calculating the block size, and then depending upon the block size, we will divide the plain text into those many blocks, and then encrypt each of the blocks separately. So there is no relationship between block 1 and block 2. There is no chaining concept involved over here. But in the case of cipher block chaining, what are we doing? We are sending the output of the previous step, that is the output of the current step right now, to the input of the next step. Am I clear? So there is a chaining, or we can say there is a relationship between the present round and the previous round, and even the next round. So all are linked together through a chain. Clear? Similarly, there is a third one, cipher feedback mode. So whatever output we are getting in one of the rounds, out of those, 8 bits are sent as input to the next round, and that will be used as input for the remaining process as well. But the only drawback of that is if any small change happens in one of the XOR operations, it will be propagated to the next rounds also. So to avoid that, in the fourth mode, that is output feedback, we totally ignored that by sending the output of the encrypted S bits instead of sending the cipher. Clear? And we saw at the end there is a totally different sort of a mode which is not depending on any of the previous blocks. That is what we call as counter mode. In this, it uses counters or sequence numbers which are then used to encrypt the plain text, and the same thing is used in the decryption side also. So I hope you got the understanding. This can come for a 10-mark question, or if any one of the modes are asked, it can come for a 5-mark question as well. Clear with this? Can we move ahead? The next topic is nothing but the most important topic of your syllabus, one of the most important topics, which is data encryption standards. But before data encryption standards or data encryption standard, we must know what exactly is the foundation of this cipher. What is this cipher and how is it different from all the existing ciphers we have studied so far? Okay, so just have a look at this cipher. It is going to be a long ride. Don't worry. We have to repeat it many times, I guess, because it might get confusing at one point of time. So kindly let me know whenever you are facing any issues, any doubts. If any step is not clear, kindly let me know. I will repeat it as many times you wish. Fine. So just have a look at this diagram and try to see what is happening. Have you heard about this concept anywhere? Because right now you're in third year, and those who are interested in cybersecurity must be aware of this. Data encryption standards. Right now, DES has been cracked. Just for your information, DES or data encryption standard has been cracked, but still there are many ciphers, for example, advanced encryption standards or AES. That is what we are going to learn next. They are not cracked yet. It is possible that one of the versions of that algorithm is cracked, but the most secured versions are still yet to be cracked. Fine. Am I clear? Fine. So any idea, any one of you is having any knowledge about what this encryption is all about, what data encryption standard is all about, kindly let me know. Any one of you. Or if you're not having any knowledge about it, kindly let me know that also. We don't know, sir. No idea. Fine. Okay. No issues. No issues. I'm there to teach only. Okay. See. So if you see at this particular diagram over here, it is what we call as a Feistel structure. If you see the heading of this lecture, I have mentioned Feistel Cipher and data encryption standard. Why so? Because this data encryption standard is again depending upon a structure that is what we call as Feistel Cipher or Feistel structure. The diagram you can see over here is nothing but a Feistel structure. Just have a look at this Feistel structure first, and then everything else we can study later on. Fine. So what happens in the Feistel structure is, as you can see, left hand side is all about the encryption part. So let's focus on the encryption first. The plain text, it's of size 64 bits. So I'm writing it over here. The plain text is of size 64 bits. Those 64 bits are first of all divided into two parts, the left plain text and the right plain text, which are of equal size of 32 bits each. Now what happens is, as you can see, some operations are performed where this f is nothing but a function block. Now we are talking about round number 0, or we can say round number 1. You can start with 0 and go till 15, or you can start with 1 and go till 16. Total 16 rounds take place. A total of 16 rounds take place, and at the end of the 16th round, we will get the cipher text as, let me show you, as you can see at the end, fag end of the 16th round, or you can say end round, general rounds, we will get the cipher text in the form of encrypted text. Fine. So what happens is LPT and RPT, or the left plain text and right plain text, are subjected to certain operations. Now, what are those operations? This is your round number 1. This is your round number 0. So what I can say is, let me write round over there, otherwise you will get confused. Okay, round 0, round 1. So what happens is, in the round 0, the R, that is the right plain text, is sent as it is without any change as the next LPT. So what are we doing? Any one of you kindly let me know. What are we doing exactly? The left plain text, that is LPT of n, is nothing but RPT of n minus 1. Yes or no? Am I clear? Kindly let me know about that. Yes or no, students? Whatever I have written over there, is it clear? Yes, fine. Okay. Yeah, I will repeat, Harsh. Just have a look. That's why they are color coded. As you can see, the main text, the initial text is divided into two parts, left plain text and right plain text. The left plain text of round number 1, isn't it same as the right plain text of round number 0? Yes or no? I have simply written it as it is without any changes. Yes, correct. So that is why I have written this formula over there. Left plain text of n is nothing, n stands for the round number, is nothing but RPT or right plain text of the previous round. Clear? In the same way, you can say that RPT of n, what will that be? Come on, now I am expecting answers from your side. What will be the RPT of n or round n? It will be, come on, check the diagram first. Check the diagram again. As you can see in the diagram, there is one XOR operation in between. Yes or no? This XOR is getting two inputs. One will be L0, that is nothing but, I'm writing it over here. L0 is nothing but L of n minus 1. Yes or no? XOR the output of this function. Yes or no? So this function will be made up of K0, or I can say Kn minus 1, comma Rn minus 1. Yes or no? I will write it once again clearly, but have a look. Just try to get the understanding of what I have done exactly. Are you getting it or not? Yes or no? Correct? So it is basically the previous round's left plain text XOR with the output of the function block. In simple terms, I can say that the, the right plain text of this round will be the output of, or whatever you can say, output of the XOR operation between the previous LPT and the function. Am I clear? Yes or no? Simple. Yes, B division. Okay, fine. So what can we say now? Any deductions, any summary? We can say that all the operations are being performed on the right plain text. Yes or no? Yes, come on. All the operations are being performed on the right plain text, which is then XORed with the left plain text. Correct. So we are going to perform some operations inside that F block. Now we are going to learn in detail whenever we are going to start with DES that the function block consists of n number of operations. It requires some key, it requires an input, right plain text, and whatever is the output of that phase or that function, that is XORed with the left plain text, and the result is sent as the new right plain text. Am I clear? So we can say that after each round, there is an operation which is swapping. Isn't it clear? So after each round, we are simply swapping the left plain text with the right plain text. This process keeps on continuing till the 16th round. And at the end of the 16th round, we will get the answer. Am I clear now? Fine. Can we move ahead? The same thing I have summarized over here. You can read it. I will not read the entire things, but only thing is over here, just have a look. The input block to each round is divided into two halves that we have seen. That can be denoted as L and R. In each round, this is very important. Don't get confused over here. In each round, the right half of the block R goes through unchanged. What is the meaning of this? Although I have told you that all the operations are performed on the right plain text, but the right plain text itself goes unchanged as the new left plain text. Yes or no? Yes, students? Yes, as you can see, the right plain text itself is going unchanged as the new left plain text. Am I clear with this? But at the same point of time, all the operations are being performed on the right plain text only inside the function block. So this is where the things start a little confusing, but no issues, no worries. I will focus on each and every part individually. Don't worry about it. If you face any issues, do let me know. Fine? Fine with this so far? Can we move ahead? Fine. So this entire process will keep on continuing till the 16th round, and after the end of the 16 rounds, you will get the ciphertext. Now the entire process in the reverse order will give you the plain text back. As you can see, the diagram is exactly same, exactly similar, we can say. The only thing is, in the case of decryption, that is the ciphertext will be the first input. It will be divided into right plain text, left plain text, and the entire process will keep on continuing in the reverse order. Right? It should be LN01. It should be left first and right first. Don't get confused. There might be some issues with the diagram. Fine. So whatever answer you're getting, the same answer you have to take and carry on with the process. Am I clear? It's basically this one only. Whatever answer you're getting over here, that same answer is copied over here. That is why they have written ln plus 1, rn plus 1, ln plus 1. Otherwise, it is the left part only, it is the right part only. Am I clear? Yes or no? Whatever ciphertext you're getting, divide that into two parts and repeat the same process again. And at the end, you will get the plain text. Clear? So this is the entire process. I will obviously share the PDF with you with the theory part. So I'm not focusing on this theory. The same thing I have repeated. Okay, the same thing is given over here. Fine. Now let's start with the basics of DES. Obviously, we can't end it in this lecture. It's going to take some time. But let's start with what exactly is data encryption standard. It comes as a sure shot question. Either it may come in options or it may come along with AES and you have to attempt any one. Fine. So just have a look at this schematic diagram, or you can say a conceptual view of data encryption standard. The data encryption standard, the data encryption standard basically consists of this view. The input is in 64 bits as plain text. Now you might see a difference over here. Can any one of you tell me what is unfamiliar or what is different in this case? The diagram looks very simple. 64-bit plain text that we have just now seen. It goes inside the DES encryption algorithm and we get a 64-bit ciphertext. But can you point out anything unusual in this? Size of the key? Yeah, the size of the key is fixed. Correct. Correct. Key and plain text size are different. That is the main thing over here. As you can see, the plain text is of size 64 bits. It is a standard, so we can't change anything out of it. It is of fixed size only. The key size is 56 bits. So here is where the things change. Fine. I will tell you what exactly is this all about. What happens is the initial key is of 64 bits only. But what happens is every 8th bit is selected and discarded. Why we are doing so is every 8th bit is used for parity checking. Now you know what is parity, odd parity, even parity, error correction, error detection, right? Every 8th bit is saved for parity checks, and they won't be used in the encryption or decryption process. Am I clear? Any one of you is having any doubts? Kindly let me know. I can see one raised hand. So in case you are having any doubts, kindly let me know. Am I clear? The initial key is of size 64 bits only, but every 8th bit is selected and discarded. Discarded as in they are kept for parity checks, just to check whether any issue is found in the bits or if there is any burst error or any errors due to 1 or 2 bits. That is the thing we had seen in the previous case also, the OFB mode, right? Similar thing. Hush, it is going to be same. You will see what exactly I'm talking about. Let me come to the exact algorithm. You will get a clear picture what I'm talking about. Is the key same or is the key different? You will come to know. Fine. We start off with a 64-bit key. That you can see this is as a conceptual view of DES, as in each and every plain text, whatever is the size of the plain text, that will be divided into this many part. Fine. And then based upon that, obviously each and every block will be having the same key. Why so? Because it is a symmetric cipher. In simple terms, I can say that each and every blocks you can see over here, they will have the same key, but still the ciphertext will be slightly different. How? You will come to know later. Fine, because we are having 16 different rounds, and in each of the rounds it entirely changes. Although it has been cracked, but at the time it was designed, it was a really great algorithm, really great cipher, which took a lot of years for the attackers to crack. Fine. So this is the conceptual view. The original key size is of 64 bits, but whenever there is a question in the exam, you have to say that the key size in DES is 56 and not 64, because those extra 8 bits are never used in the encryption or decryption process. Am I clear? Fine with it? You may have MCQs also on this. What is the key size in DES algorithm? The answer should be 56 and not 64. Fine. Shall we move ahead? Yes or no? Okay, fine. So now what I'm going to show you is the actual diagram of DES, the detailed steps in DES. Detailed. Okay. So what happens is there is a 64-bit plain text. I'm talking about one of the blocks. Okay. You might have 1,000 bits of plain text, and again the same process. Divide the 1,000 by 64. Those many blocks you have to use for the plain text. Fine. Use for the encryption. So I'm just talking about a single block over here. That single block of plain text of size 64 bits, it has to go through a process that is what we call as initial permutation. We'll see each and every one of those processes later on. First of all, tell me what is permutation. We have already seen what is permutation. Any idea? Kindly let me know. We have already seen the definition of permutation during transposition ciphers. Any idea you know what exactly is permutation? Come on, let me know the answers. Try to recollect what we had done in the case of transposition ciphers. You will get the answer. Yes, come on, quickly. What can be permutation? We had seen in the case of rail fence cipher also. Correct. Changing the position of the text. It's very simple. How many times I need to repeat it? Shuffling. Correct. You need to change the positions of the text without substituting it with any other values. You have to simply change the position of first bit to 10th bit, ninth bit, whatever it is. Right? That is what we call as transposition, or that is what we call as permutation. Fine. So that is what we are doing over here. The initial 64-bit plain text is subjected to an initial permutation. Why we are doing this? We are basically doing this to randomize the plain text. We don't want the attacker to straight away attack the plain text. We want it to be in a randomized format so that it becomes a lot more difficult for him to crack the cipher. Am I clear? After the initial permutation is done, we have to start with the Feistel architecture. If you remember the Feistel cipher, we divided the plain text into two parts, left plain text and right plain text. The same thing happens over here. And once that is done, we have to repeat the entire process for 16 rounds. Now I'm coming to the question which was asked by Harsh, I guess. Is the key going to be same or different? Obviously, the overall key that is being sent in one of the blocks, it is going to be same as 56 bits, but the internal operation is somewhat different. You will be having 16 different keys for each of the rounds, and those 16 different keys will be produced by a method which is what we call as key transformation. I will start with the detailed explanation in the next lecture because it is going to take a lot of time, so I don't want to start it and leave it midway, right? So I hope I am able to answer your question, Harsh, I guess. Yeah, Harsh Chauhan. Fine. So overall, if we see from the conceptual view for point of view, the key is going to remain the same for a single block, because if we see the decrypt, if we see the attacker is not having access to the keys. So whatever key the attacker will gain access to, it will be the 56-bit key only. So the keys are going to remain same. But internally for each of the rounds, there will be different keys which are going to be used. Fine. I will show you how those keys are generated and how those are used for encryption. Fine. Okay. So after the end of 16 rounds, you are not still having the ciphertext ready. What you are doing is you are performing one final round, which is what we call as final permutation. Again, similar to your initial permutation, we have to do the same thing. That is again change the positions of the text based upon some table. Now, whenever I'm saying a table, it would look something like this. In the 1 comma 1 position, you might have a value as 17. In the 1 comma 2 position, you might have a value as 21. So what we are doing is we are replacing the first character over here with the 17th character of the ciphertext. Am I making any sense? Whatever character you are having at the 17th position, you are picking that up and placing it in this particular location. That is 1 comma 1. Similarly, whatever character you're having at 21st location, you're picking that up and placing it in this location, that is 1 comma 2 location. Am I clear? So I will show you the tables. One more thing, you don't need to by heart the tables. It entirely it's entirely up to you, but you don't need to by heart the tables. If you show some random values also in the exam, that is also accepted, because it is not expected that you will be mugging up or you will be remembering each and every value of that table. Am I clear? Fine. I guess you understood how the transposition or how the permutation is done. Fine. And at the end, you will get the result as a 64-bit ciphertext. Fine. The same thing I have summarized over here. Just have a look. Divide the plaintext message into blocks of size 64 bits each. Subject it to initial permutation. Divide the plaintext block into two equal halves. LPT, that is the left plaintext, and the right plaintext goes through 16 rounds of encryption process along with 16 different keys for each of the rounds. After 16 rounds, the left plaintext and the right plaintext gets combined, and final permutation is performed on these combined blocks. The final result or the result of the final permutation produces the 64 bits of ciphertext. Am I clear schematically? I hope so. You got an understanding of what exactly this cipher is all about? Yes? Kindly let me know if any doubts are still there. Yes or no? Fine. Okay, because this is a very crucial cipher. If you face any issues, any doubts in between, kindly let me know. I will repeat that. No issues. Fine. So just have a look. This is the overall process. I will start from the next lecture, but I'll just giving you a gist of what exactly is going to happen. There is a 64-bit plaintext, and that 64-bit plaintext is divided into two parts: LPT, RPT. Internal structure will be the same only. This is what we call as the function. If you remember, there was an F block, yes or no, in the Feistel architecture. This is what happens inside that F block. There is a process called key transformation. There is a process called expansion permutation. There is a process called S box substitution and P box permutation. So after all these processes are done, the output is then XORed with the LPT, which becomes RPT of next round. This is what we had seen in the Feistel architecture, yes or no? The same thing, this particular scheme over here, as you can see, the F block, one input goes inside it, that is being the output of that particular function is XORed with RPT and so on, LPT and so on. Fine, the same thing. So these are the four operations that take place inside the function block. So we are going to study all of these in the next lecture. The very first thing is you have to divide the entire question. It comes for 10 marks minimum. So you have to divide the entire question into different sections. Draw two diagrams at least, or at least a single diagram. One single diagram which can explain the entire process. If you draw it carefully, then it's fine. No issues. Sometimes it was asked for even 20 marks. So it depends upon the weightage of the question. Depending upon the weightage, you have to attempt the questions, attempt the answer, and write accordingly. Fine. Any confusion with this? I will obviously share the notes. As you can see, the length of this answer is, I guess, too huge, but I have written it from an explanation point of view. You don't need to write this much. Just have a look. This is what I'm going to share with you so that you don't need to refer any other notes, any other book. Fine. I have added some extra diagrams also just to make you understand the things. Don't get afraid, it's very simple. I will explain each and every one of these diagrams, each and every one of these steps one by one in detail. Fine. So at the end, you will be able to understand this. You should be able to. Okay, fine. So can we end this lecture over here? If you have any doubts, you can ask me. Let me drop in the attendance link soon. Okay, we still have 5 minutes. So if you have any doubts, if you have any queries, if you want me to explain any one of the topics, you can ask me. I'm not starting with the main rounds. I will simply show you how the initial permutation table looks like. Just have a look. I'm not starting with the main rounds or main functions. Simply have a look at this initial permutation table. Can any one of you tell me what exactly is happening? Can any one of you tell me what exactly is happening inside it? How many bits are there? Yes, students, D division, A division. 32 bits are there, I guess, no? 8 into 4, 32. Don't count the values. 64 वैसे मत गिनो वैसे मत गिनो कितने positions है? How many positions are there? 32, right? Okay. Now see what is happening. The initial permutation. If you check over here, if you check this diagram, this one, what is happening is the 64-bit plain text is subjected to an initial permutation. So हम लोग क्या कर रहे हैं यहाँ पे? What we are doing is we are dividing the plain text into two parts, LPT and RPT, right? So this is the same process. What we are doing is based upon some table, based upon some value, we are changing the positions. So what we are doing is, I guess I think this is the half table. I'm not having the complete table right now. I will show it to you in the next time. In the next lecture. It is basically, it should be 64 because we are having a complete 64-bit plain text, right? So in this table, you are simply having 32 bits. So I'm showing only the RPT part because all the operations are performed on the right plain text, right? Yes or no? Correct? Ideally, it should be 64, but I am focusing only on the RPT part. So you can say that after the initial permutation, this is what happens, that the 48th bit of the original plain text comes to the first bit of the RPT. Am I clear? What we are doing is we are replacing the first bit of the plain text with the 48th bit. Whichever bit is present at the 48th location, that will now be my first bit of the RPT. Am I clear? Yes or no? Similarly, the 57th bit will now be my second bit and so on. So it is the very first step that after your plain text is created, you have to convert that into a permuted table. Jimmy, that is what I'm saying. It is ideally fixed, but it is not expected from you to write the entire table as it is, because I know you won't be able to memorize so many values. So it's fine if you add any random data over there, but just make sure the limits are maximum till 64, because we don't have any positions after 64, right? So it will start from 1 till 64. Fine. Inside the table, you write any values, it's acceptable because it is understood that you can't memorize so many values, positions, and on. Fine. Am I clear? So from this point, we will be starting in the next lecture. I will tell you what exactly is the entire table, 64-bit table. This is ideally the 32 bits shown to you. Fine. Okay, so at this junction, I can stop this lecture. In the next lecture, we'll resume this particular topic. Okay. Thanks a lot. Thank you.